In this video lesson, I am going to bring in an example where anyone viewing this can learn to apply our understanding about, we can apply our understanding on how to find related rates to a problem in business right here, to an application problem in business. Okay, so this example is intended for students, calculus students who are on track to business field, or on track to a business major or econ major over here. However, any other calculus students outside of those academic terms can also, however, any calculus students outside of the business field or outside of the econ, the major can still view this as an extra example to understand how we apply our understanding in finding related rates. Okay, so let's now spend some time reading the worded description of the example. So a company's revenue from selling Q units of a product is given as, so what clicks my attention here is we have an equation. Okay, and so in this equation, one thing I have to be clear with anyone viewing this lesson, that we don't have, in our role working on this problem, in our role, in our position, we don't have to worry about how that equation was derived. Okay, we don't have to wonder how that equation came out. This equation, R equals 1000Q minus 2Q squared here. This equation, think about it, was the job of an analyst who that company hired to observe market, okay, and come up for us. But let's understand a little further about the equation once it was given to us to work with as we take on to the next step right here. So right from that equation, the beginning description was talking about the revenue. So it makes sense that in this equation that says R equals 1000 Q minus 2Q squared, it makes perfect sense that this R right here is a variable for revenue. So clearly R is revenue, because that's directly associated with the description that's stated in the question, in the problem. So the revenue from selling, okay, Q units. That's it. That's how we recognize the information. And so in that way right here, the problem also used the problem, the kind of reveal the name for what that variable Q is for. Okay, to reveal the meanings that the problem, the worded description of the problem revealed the naming, the meaning of this Q variable is for. That Q variable in our equation is the number of units. Okay, or this is the sales quantity right here. And here now we're talking about, if it's a company, we're talking about it's a large scale sales right here. So Q is a sales quantity. Now I'm using that formal term for a large scale sales again. Okay, so Q is for sales quantity, the number of units being sold. All right, and so again, I'm asking anyone who is following along with this lesson to not worry about how this equation came about, how this equation was derived. Okay, that belongs to the job of an analyst, where that the company hired to observe markets and come up with this for us. What we do here is that we're gonna take that, assuming the analyst already properly check his math work and all that and derive the correct equation. Okay, we take on and analyze that equation. Okay, so think about if we run a business, we are we are a strategist. We come up with strategy to improve our revenue. So in that way right here, the revenue come out from an analyst. But once the analyst handed this equation to us, we take that equation and work with that to come up with different strategies to study about the revenue of our company. Think about you're one of the leader or the CEO of that company. Okay, you want to work with that revenue that your higher analyst gave you. Okay, and you work with that and you want to improve your company. Okay, so now in this way right here, let's get back to the worded instruction of the problem, the worded description. So after knowing that we have an equation relating the revenue with the quantity right here, it's an equation that relates between revenue and quantity. Revenue is in R and quantity is in Q right here. So let's continue reading. If sales are increasing, at a rate of 60 units per day, all right, so immediately it clicks with my, immediately it caught my attention here with that phrase per day right here. So now allow me to undo the highlights right here and just right now focus right on that term per day. Okay, that means that term right here refers to we do have a time variable existing and involved in a problem. It's just not directly present here. It's not currently present in this equation. This equation only relates revenue and quantity. But surely, according to the information I highlighted, so now I'm going to name that T. We have our choice of naming a variable as well. So I'm going to name T as the time variable, because see that phrase I highlighted, per day. Okay, so time, there's a time variable, okay, involved. But again, keep in the back of your mind, it's involved, but not directly present or not currently present in this equation. It's involved implicitly. So that means any one of these variables here, the R can be eventually a function of T, and Q here can also eventually be a function of T. R is a function of T, and Q is also a function of T. These are both variables in our equation, but now each one of these is a function of T. Okay, because there's a time variable involved here, and I pointed that out through that keyword. You know, the sales is increasing at a rate of 60 units per day. That phrase per day that I underlined, that I highlighted right there with this highlight information. All right. So now after ringing up that bell right here about we have another variable involved, the time variable involved in a problem, let's continue reading. So now I'm going to complete the statement here. If sales is another way of saying the quantity being sold over here, the quantity, the number of units being sold. That's what sales is all about. So and that's how, you know, the professionals in business fields are understanding it, are communicating. So if sales are increasing at a rate of 60 units per day and then increasing, okay, so that's all of those highlighted information together is indicating for me what we have here is a rate. See, rate of 60 units per day. That means now, as far as the given information, we have the Q, dt. See, rates now is increasing at 60 units per day, and so right on that, right from what caught my attention, the term per day refers to, you know, our rate of change are in respect to the time variable. That's why now I can legally write dq dt, because of that phrase, you know, 60 units per day right there. Okay, so day is the units for time, and then that's indicating we have a rate, that the rate where our quantity is changing, but as changing over time or relative to time or in respect to time. Okay, so now clearly there's so many ways we can understand that clearly we have a dq dt given 60 units, okay, per day. That's the quantity. I mean, that's the units per day. But in a more general understanding, I see this as a rate of change here. And now a little further into the problem, what caught my attention is that the sales are increasing. Okay, so we got a change, and that's why we have a rate. But then the change here is an increasing change here, a change that increases our sales. So sales are increasing. That means this quantity, this rate right here is a positive rate. This rate of 60 units per day right here is a positive rate. All right, so now I have, well, that sign is already proper. It's positive 60 units per day. So we got dq dt. Okay, and so now back in the problem, and then let's continue reading further to see what the question is, what the problem is asking for. So now getting into the actual question, how rapidly is revenue increasing? This is just a different term for saying how fast is revenue increasing. Okay, revenue increasing, but how fast? And as I said earlier, how fast, how rapidly is a different way of saying how fast. That means we are, mathematically speaking, and together with our understanding in calculus at this point, how fast is revenue increasing? We refer to, from this problem, we refer to, that refers to let's find the change in revenue as a rate over time. How fast? Okay, dr dt. And so I already pointed out earlier that any of the change in this problem is referred to is in respect to the time variable that's implicitly involved here. And that's why, and earlier I explained that right here in this example, in this problem, that the change in sales is a change in respect to the time variable. It's a rate in respect to the time variable. And so the same with the change in the revenue. It's a change in respect as a rate of change in respect to the time variable. So that's why I ended up with dr dt here. And so now, particularly right from the way how the question is worded, how fast, how rapidly is the revenue increasing? Okay. Another way of saying we're looking for dr dt. All right. There are still more information. But I'm going to get back to that and extract more information, more given information later. We have enough leading clue to start getting into finding finding the related rates here. We have two rates involved. One rate is given, and the other rate we need to find. And our equation that concerns us right here, the equation that concerns us, the analyst of the company gave this to us right here. That equation that concerns us, or equals 1000q minus 2q squared right here. Okay, and again, nowhere in this equation that I spotted the t variable being indicated, but I know the t variable, the time variable, is being involved in this problem like that. All right, and so now in that way, this is where I bring in my understanding about finding the related rates right from this equation. Okay, so I'm gonna go to my other board space right there. All right, so now with our equation written as r equals 1000q minus 2q squared. 1000q minus 2q squared. I'm about to find the related rates right out from this equation. I'm about to find all of the related rates because so far this equation only relates my variables. Two variables mainly involved in this equation. The revenue and the quantity. Only those two variables. And we know that we're about to work with the two rates, the dq dt and the dr dt. And so just like in any explanation I've had throughout other examples and the same thing I can mention here, the time variables that we're doing, even though we know it's involved, but it's not directly present here, and then our derivative, our rate of change was clearly stated that we're working with dq dt. See, so we're treating q as a function of t implicitly, and then we find dr dt, and then these are all rates in terms of t. That means right from this equation, this is where we bring our understanding about related rates in right here. We're gonna differentiate. This is the term I used in a general lecture about the related rates right here. I'm gonna differentiate both sides of this equation in respect to or in terms of the t variable, because we know that our goal is to work with these rate of changes in terms of t variable. All right, so now I'm gonna differentiate both sides. But how about, before directly getting into it, I'm going to just write down the goal over here. We want to, in the next step, we want to differentiate in terms of t. So, in case you have seen some other examples of mine prior to this one right here, some of the other examples I didn't write down in words this goal of our next step right here, but instead I'll just go straight into the problem. But here I decide to write down the goal of the next step instead of rushing immediately into doing the work. Here's my reason. Okay, if we look back at this equation one more time, okay, I notice R itself right here, and I'm talking about before we differentiate in terms of t. Before we differentiate this equation in terms of t, I know this, okay? I know this as an observation. How about, so let me write it in this little corner of my board right here. R, in this equation I noticed, or I observed that R is one variable, but it's already written as a function. It's already expressed as a function of Q right here. Again, what I just said, this equation that we're working with already expresses one variable as a function in terms of the other variable. See, F here is just my comfortable notation indicating it's a function of Q. See, R here clearly one single variable R, coefficient 1, R equals all terms on the opposite sides or in terms of Q. And that's how I see that this equation expresses my variable R as a function of Q. Or more generally, this equation already expresses one variable as a function in terms of the other variable. All right, and so now to proceed and to make the process, the rest of the work here easier, allow me to approach in one direction right here. I mean, at this point, seeing this equation, there are many directions to approach, but I believe prior to viewing this example, any one of my students have seen a separate lecture where I introduce a special case that from that lecture, I introduced the case that anytime we have our equation already expressed, one variable as a function in terms of another variable, okay, one variable already expressed as a function in terms of the other variable, then we have some advantage. So yes, you can just directly differentiate both sides in terms of t as this goal is indicating. But now, after viewing that lecture of mine, okay, allow me to approach in that way that can save some effort for us. I see this is a function of Q. So now to find the RDT, yes, differentiating in respect to t right here, I notice that R is a function of Q. So now I'm according to the chain rule, and this is information I explained in that lecture right here. I can quickly do dr dq. This is a rate of change relating between R and Q. How fast, how quickly R is changing in respect to Q, the quantity. So this is a rate between the change in R versus the change in Q. But then according to the chain rule, we're going to multiply with the rate dq dt. All right, and so I had the complete detailed explanation in that lecture where I pointed out how chain rule can be seen as related rates. This comes right out from that understanding. And so the reason I can use that understanding from that separate lecture there is simply because right from that key observation right here, I observed that this equation already expressed our variable R as a function of Q. That's why differentiating in terms of t really is just applying the chain rule. We want to find the derivative dr dt, and that is equal to dr dq. This is the derivative of the outer function, the outside function, multiplied with the derivative of the inside function. Okay, so if you're not sure what I'm talking about in this particular related rates equation right here, view the lecture of mine where I specifically mentioned about how any chain rule or how chain rule can be seen as related rates. Okay, so now allow me to assume that you already had that background after viewing that other lecture of mine right there, that independent lecture of mine. And so now from that equation, how is this usefulness in our work right here? How is this useful? I mean, how is this useful in our work? So the big work here, and after what I explained in that video lecture there, then the big work here is just to find dr dq. But see, wait a minute, dr dq is so ready for us here because we have that advantage. R is already expressed in terms of Q. So dr dq is easily 1000 for the first term minus, we want to find the derivative of R in terms of Q. This is what dr dq is, and I'm on my work to find that. So I'm going to subtract 4Q. This is my dr dq. And then in the next step, I'm going to multiply with dq dt, and that equals dr dt. But ladies and gentlemen, this is how I have come to derive, this is how I have come to find my related rates. Okay, I have found two rates. I have found a relationship, an equation that's relating the two rates right here, the rates dq dt that's given in the problem, and the rates dr dt that we're supposed to find. And this was indeed another rate right here. This is the rates dr dq that we already know to express that as 1000 minus 4q. This is a related rate. This is an equation that points out, that relates all of the rates in our problem right there. Okay, that's how I said I have found all related rates in this equation. All right, so now at this point right here, we know that we were given with dq dt to be positive 60 units per day. That's dq dt, it was given. We need to find dr dt. All right, and so right in this equation, I am ready to substitute dq dt with 60 right here. But now let's hold it. I realize one further thing. Once we substitute dq dt with 60 right here, then we're still going to get stuck with that variable q, because we need to also know a quantity of q right here. I mean a value for q right here. Okay, and this is the reason why. Now let's turn back to the worded description on the computer to find out if we have any clue leading to some value of q right here. All right, so now back to the worded instruction of the problem right here. Let's continue reading. So we want to find how rapidly is revenue changing. Okay, how rapidly is revenue increasing when 200 units have been sold. All right, so this information just now this information that just now I highlighted, okay, indicated that we have a given quantity, a given value for q right here at that particular instance. So now allow me to write down that information here. So aside from having this given information being dq dt equals 60 right here, I have another one. I have another given information. How about q at that instance? Q equals 200 and just 200 units. So now we want to find the rate of change of revenue right at that instance where where sales quantity reached 200 units sold. All right. And so now at this point we have all that information we need right here. dr dt is what we are looking for, is what we are finding. That equals, now in parentheses. Now this time allow me to use brackets here because I'm about to substitute in some values inside of the parentheses. Okay, so 1000, I'm going to subtract 4 times 200 because this 200 is the quantity that, or 200 here is the value for quantity right here. It's an instance. Okay, it's an instance where our revenue, where our quantity reached 200 units sold right here. So at that instance, we want to find out what's the rate here. Okay, and calculus that you're learning is all about, we want to find the kind of rates that happens only at an instance. And so that instance is indicated right here, the instance where our sales reach 200 units. Okay, so 1000 minus 4 times 200 in parentheses, but then all of this in another level of parentheses multiplies. So at that instance, we're looking at dq dt being 60. Okay, positive 60 substituted for dq dt. So now all of a sudden, if we're having a closer look, we are so ready for coming up with a final answer here. Okay, it's just a matter of running it through a calculator. Okay, so now I'm going to swing over to my computer station to grab a calculated value. All right, so my final calculated answer came out being, according to my calculation, my final answer came out being 12,000. Okay, 12,000, and this is a revenue. Okay, and it's a rate of change for revenue, in respect to the time variable. And so this is 12,000 per day. Okay, and I'm slowly putting in, and it's dollars because it's money, it's revenue. Okay, $12,000 per day. But here's the thing, let's look even further. Now when it comes to rate of change and in a practical situation like this, we need to know, are we increasing or decreasing? If it's a positive sign, if the problem was a positive sign, okay, that means it's increasing. Positive sign, that means it's increasing. Our revenue was increasing at a rate of $12,000 per day, right at that instance where our company reached 200 quantities sold, okay, for Q. All right, and so just now I made that statement clearly stating that the quantity, the revenue here is increasing. The revenue is increasing. That's making it consistent with another piece of information in a question that may not catch, that may have not caught anyone's attention right here. But how rapidly is the revenue increasing? So this piece of information was already giving a clue ahead of time before we even tackle down the problem that the final revenue, the final rate of change in revenue is already expected to be positive right here. Okay, but if we didn't catch that information, that's completely fine. Our final answer already showing something consistent with that is a positive quantity right here. All right. And so now I am going to put this, and I don't think we need to write that positive sign right here, making it look a little too busy. Okay, so now that's all of that. Here is our rate of change for revenue. We keep getting larger, we keep increasing our revenue, okay, at that rate of $12,000 per day. Okay, in the way, if the analyst, whoever gave us this equation being a true equation, okay, if that equation truly is the correct right there, then our revenue would be increasing at $12,000 per day right there. All right.